All right, so now I'll briefly introduce some of the salient points of this chapter. So if you have an isolated system and you do not have any external forces acting on the system, then over several chapters we learned that the energy of the system is constant. Do you guys remember anything else that is constant?
Momentum.
Very good, my friend. Linear momentum was constant. The linear momentum of the system was constant. And today, we'll learn a new quantity called angular momentum, denoted by L, and that will be constant. Okay? So, what we are saying is, okay, so no matter how complicated the motion of the system is, you guys remember we saw a video of a pool rack being broken, and through the entire complicated motion, before it was broke, the rack was broken, and after it broke, the linear momentum was conserved. Similarly, angular momentum will be conserved. Okay, so here are some powerful quantities that we are introducing that remain constant throughout the complicated motion dynamics of a system, okay, assuming certain conditions. Okay, so that's sort of a deep point. Yes, so more point that's relevant to you guys will be the following. Okay, so do you guys remember what is Newton's second law? Force equals mass times acceleration. Okay. So this was valid under special circumstances. What is the most general form of Newton's second law?
Derivative of the momentum.
Very good, my friend. Very good. Okay. So this is the more general form of Newton's second law. This was valid when dm by dt was 0. Okay. So this was equal to dm by dt times velocity plus m dv by dt. Okay. So this was equal to that. And when this was 0, this reduced to that. So this was a special case. Okay, so similarly for rotational motion, last time you saw that tau was equal to I times alpha. Okay. This was the special case. Moment of inertia was the parallel of mass. And when the moment of inertia does not change, this is valid. This is Newton's second law for rotational motion. So today we'll see the more general form of Newton's second law for rotational motion is this, where L is angular momentum. Okay. So just like Newton's second law, d by dt, angular momentum can be written as I omega, di by dt omega plus I times d omega by dt. Yeah. And this is equal to alpha, this is equal to that. So this reduces to that when di by dt is 0, okay, when the moment of inertia of the object doesn't change. And you saw that when the moment of inertia of the object changes when the mass distribution changes. Okay, so for instance, a skater, when he or she pulls her arms in, what has she done? She's decreased moment of inertia. Okay. And so in circumstances when moment of inertia changes, this term will not be 0. Okay, so that will be one of the main points we learned today. Okay, and there'll be many things to learn, but so this is Newton's second law for rotational motion. L is the angular momentum. Okay, and that's the title of the chapter. Okay. All right, so now that we know where we're going, let's get into the slides. Okay. First, we'll introduce something called rolling motion. Okay. What we're interested in is a wheel rolling without slipping. Okay? And you do this all the time. So when you drive your car, your wheel is rolling. Okay? And so let me show you a little. Okay. So here is a wheel that is rolling without slipping. Okay? And you can see that if you have a point on the rim, the point on the rim, what it describes is a curve called a cycloid. Okay, so this is a wheel whose center of mass is traveling at a constant speed. Okay, and the point is describing a cycloid. Okay, here is a wheel that is rolling without slipping. So let's do an extreme, other extreme. So if a wheel does not roll and it just slides. So here I'm going to demonstrate a wheel just sliding. What is that point describing? Yes, straight line motion. Very good. Okay. So when a wheel is rolling without slipping, that point is describing a cycloid. Okay. So that's what we're interested in. And what we're going to show you is that a rolling motion without slipping is a combination of pure rotation, this is pure rotation, and this is pure translation. Okay. So rolling is a combination of pure rotation and pure translation. So that's what we'll see in the first few slides. All right. So these are some of the other topics we'll talk about. Rolling as a translation and rotation combined. We'll talk about angular momentum. That's the hero of this chapter. Okay? Angular momentum is a vector and denoted by L. And you'll see it's a very, very fundamental quantity. Okay? So conservation of angular momentum. So here is what this means is the following. Okay, conservation of angular momentum means angular momentum is constant. That means dl by dt is 0, and that's true when there's no torque acting on the system. Okay, so if there's no torque acting on the system, then L will remain constant. Okay, and we'll see tops and stuff like that. Okay, so you saw that when a wheel rolls, a point on the rim describes a cycloid, okay? And that's the axle going at constant speed. Okay? Paths traced by points on the rim of a rolling wheel are cycloids. Okay, so here is pure rotation. So there's the axis of rotation. This is a view of the wheel, and when the wheel is spinning this way, this point is going at that speed, and this point, diametrically opposite points are going at equal speed but in the opposite direction. So this is pure rotation. This is pure translation. Every point has the same velocity. That's pure translation. Okay. Now if you add the two, if you combine the two, combining the two just means adding every velocity. So this plus that is that velocity. That plus this is this velocity. And this plus that is 0. So what that means is when a wheel is rolling without slipping, this point of contact, that is the only point that is momentarily at rest. Okay. And so if you took a snapshot of the velocities, so this guy is going at that velocity, and this guy will have that velocity, this guy will have that velocity, and so on. Okay. This guy will have that velocity, this guy will have that velocity, and so on. Okay, so when the wheel is rolling, it's rotating about this axis. Okay, and then the next point will come in contact, and that point will be at rest, and the wheel will rotate about that axis. So that's the rolling motion. Okay, but what we're going to show you is this motion. We've already shown this in diagram. This motion is the sum of this motion plus this motion. Okay? All right, so if the wheel is rolling without slipping, when the wheel rotates, so you can mark two lines, when the wheel rotates through this angle, it will have traveled this distance. If it was slipping, it would have traveled more than that distance. Okay? All right, so when the wheel rotates through this angle, the distance it travels, S, is r theta. Okay? And once you have one equation, you can do all kinds of stuff. You can, so for instance, you take the time derivative of the left-hand side, that'll give you the center of mass velocity. Okay? The rate at which it's covering distance gives you the center of mass velocity. Okay? Is ds by dt. R, the wheel, radius of the wheel is not changing, so r is constant. It will be r d theta by dt, which is omega. Okay? The rotational speed of the wheel. All right, so the center of mass velocity is r times omega. Okay. So now this formula tells you one thing. You guys have seen those cars with bigger wheels? Larger wheels? So why do they do that? The answer is in that equation. So your engine will give you a maximum rotational speed. You attach a bigger wheel, you get a larger, greater velocity, maximum velocity. What's that?
And slower acceleration.
Yeah, and acceleration. So, but your final velocity, and r omega. What our friend said is acceleration, center of mass acceleration. Okay. What our friend said is the following. See, he was 2 steps ahead of us. dv by dt is acceleration equal to r alpha. Okay. Okay. So you get greater acceleration and greater final velocity. Okay. So, oh, there it is. It's all right. So we keep saying that rolling motion is pure rotation plus translation. So what this slide shows you is the following: the kinetic energy is the kinetic. See, this is kinetic energy of pure rotation. This is kinetic energy of pure translation. So the kinetic energy of a rolling object. So it's rotating about that point, and you see here's the velocities of the various points. Is the kinetic energy of pure rotation and pure translation. Okay, what this is saying is, so I have to go over a lot of slides. I'm not going to cover everything in detail. So the kinetic energy is the kinetic energy of this rotation about that point, and that's equal to the moment of inertia, IP. What it's saying is the moment of inertia of the object about that point times omega square. Omega is the rotational velocity, angular velocity. Okay. And then this moment of inertia, using the parallel axis theorem, can be written as the moment of inertia about this point, moment of inertia about that point, plus mr squared, plus mr squared. Okay. And so that times that is that, and r omega is the center of mass velocity. Okay, and so this term becomes that. So you have pure rotational kinetic energy plus pure translational kinetic energy. So rolling motion is pure rotation plus pure translation. All right, so many people are surprised when they first learn about this. Okay. So when you're accelerating in your car, for instance, what does your engine do? All your engine does is it spins your wheels. Okay. And when you want to accelerate it, the engine is trying to spin it faster. Okay. So the engine is trying to spin the wheel faster. Okay. But friction is preventing the wheel from spinning. Okay. What kind of friction is it? See, I'm sorry?
Static friction?
It's static friction because this point is not moving. This point wants to spin that way, so the static friction force is in that direction. Okay? and that's the only point that's in contact with the car. So that static friction is what is accelerating your car. Yep. All the engine is trying to do is trying to spin this wheel faster and faster, but this wheel, if the wheel slipped, so for instance, if you were had metal wheels on an icy surface, the wheels would slip, and then you would go nowhere. Okay. All right, so it's the static friction force that gives you an acceleration. All right, I will briefly give you the derivation of this, but what we're looking at now is a wheel or a cylinder rolling down an incline. Okay. Now, before we do that, you guys saw this before. Let's say if you had an incline and ice cube slid down the incline without friction, the acceleration of the ice cube would be g sine theta. Okay, now what we're going to see is if a wheel rolls down without slipping, the acceleration of this wheel, of the center of mass, is g sine theta divided by a quantity greater than 1. So this guy will have an acceleration smaller than the acceleration of the ice cube. Okay, so if the ice cube and this guy were to race, the ice cube would win, because he's got a greater acceleration and he would reach the bottom first. Okay? Now here's the deal. Greater the moment of inertia of this guy about that guy, about the center of mass, slower his acceleration would be. When is his moment of inertia greater? When the mass is further from the axis of rotation. So for instance, this guy in this diagram, they both have the same mass and the same outer radius. This guy has greater moment of inertia than this guy. His acceleration will be smaller. So if these two guys were to race, their masses are the same and their outer radius is the same, this guy will win over this guy. Okay? So that's the deal. So let's see this. Okay, so if this guy is rolling without slipping, so it's there's a static friction force and there's the force of gravity that's acting in this direction. All right, so the net force on this guy is this force minus that force, this force minus that force, and that should equal mass times the acceleration of the center of mass. Okay, and that's what we want to find. And also, if you calculate the torque on this guy, the static friction, we'll calculate the torque about this point. So this guy will have 0 torque, and the torque of this guy will be this force times that distance, so that moment of arm. So the torque is equal to the moment of inertia about the center of mass times the acceleration alpha. Okay, and alpha is A center of mass is R times alpha. Okay, so if you substitute that there and solve and substitute for F, the static friction force there, Fs is I center of mass, alpha is A center of mass divided by R. So if you plug that in there, and this for alpha, what you'll get is, if you substitute all of that, you can solve for A center of mass, and this is what you get. Okay, so again, for an object rolling down an incline, the center of mass acceleration is decreased by that factor. Okay. So the main point is an object rolling down has an acceleration smaller than an object sliding down, frictionlessly. Okay. So, by the way, this is a bowling ball. All three masses are the same. All the outer radii are the same. And this is a solid ball. And the moment of inertia of the solid ball is 2/5 mr squared. Okay. For the disk, it is 1/2 mr squared. 2/5 is smaller than mr squared. Okay, so this guy and this guy's moment of inertia is greater than that because there's more mass distributed away from the axis. So this guy has the greatest moment of inertia. Okay, so I greatest, I medium, I small. Okay, the smallest moment of inertia will have the greatest acceleration. Okay, so this guy will reach first, this guy will reach second, and that guy will reach last. Okay. And so here is the final velocities at the bottom. Okay, after they've dropped through a height h, that's the final velocity. Okay. Anyway, here's what I want you guys to remember. When an object is rolling down an incline without slipping, its acceleration is smaller than an object sliding without friction. Okay. All right, what gives linear acceleration? Forces give you linear acceleration, okay? Just like that. And so similarly, you've learned that torques give you angular acceleration. Okay. And so here's the special case. Torque is I times alpha. Okay, again, these guys are valid when mass and moment of inertia are constant. Okay. So here's the definition of torque. Okay. So here's an object, and here's a force applied at that point. Okay, and if you can calculate the torque about any point. Okay, for this force, you can calculate the torque about any point. You can calculate the torque about this point, that point, that point. You can calculate the torque about New York for this force. Okay, so you got to remember that. Okay, so the torque of this force about that origin is R cross F. That's the definition of the torque. All right, this Newton's second law, you will learn that, yeah. We'll talk about this. So the torque depends about the point about which you're calculating the torque. Similarly, we'll define angular momentum in a second. That also depends about the point you're calculating. So this guy is valid as long as you calculate the torque and the angular momentum about the same point. Okay. So here is angular momentum. Okay. This guy is the main guy of this chapter. He's denoted by L. He's a vector quantity. So you know, if it's a vector quantity, if you have to add several angular momenta, you just add vectors. Okay. Is R cross P. P is the linear momentum. Okay, so if this guy moves this point, so when this guy is spinning and this point is moving at that velocity, his angular momentum about that point is R cross linear momentum. R cross linear momentum. And just like torque, you can calculate the angular momentum about any point. But for this guy to be valid, you got to calculate the torque about the same point and angular momentum about the same point. Okay? All right, so for this piece, the angular momentum is R cross PI. Okay. Now, here's Newton's second law. We'll derive the Newton's second law, the general case. So there is Newton's second law. That is the parallel of this fellow, dt. Okay. Force gets replaced by torque. The net force on the system is equal to dp by dt. So force gets replaced by torque, and linear momentum got replaced by angular momentum. Okay. I'm just going to go through this just because, just to show you one little trick that they have used. Okay. Before I do that, you guys know how to do cross products. Okay. And you use your right hand rule. You point your fingers, turn your fingers from the first vector. So let me draw for people I'm recording. When you turn the vector from here to there, when you turn your right hand fingers from A to B, your thumb points in the direction of vector C. So your C vector will point in that direction. Okay. I don't know if you'll remember this, but what is A cross A? Okay. So by the way, magnitude of A cross B, let me give you a hint. Magnitude of A cross B is AB sine theta. So what is A cross A? The cross product of any vector with itself.
Zero.
Zero.
Sine of equals 0.
Very good, my friend. Have I ever told you I love you? Okay. Good job, my friend. Okay, so remember that. Okay. The cross product of itself is, a vector with itself is 0. Okay, so we're going to use that little trick. Okay, to establish this Newton's second law. Okay. All right, so what we're going to do is here's a point particle. We're going to apply force on it, and we're going to calculate the torques about that point. Okay, so, and we're going to apply a force on that. The torque of this force is R cross F. But what does the force do? It gives this particle a linear acceleration. Okay, so that's the torque, and there's R. F changes the linear momentum of the particle. Okay. Now what I'm going to show you is that, well, I'm free to add a term like this, dr by dt cross p. What I'm saying is, this is the same as this plus that. When is that true? When is 5 is equal to 5 plus 0, right? So I can add anything to it as long as this is 0. That's all I've done. And now let me show you that this thing is 0. Well, dr by dt is the velocity. Dr by dt is velocity. And velocity is momentum divided by mass. Okay, so dr by dt is momentum divided by mass, but p cross p is 0. So this term is 0. And why did I add that? Well, here's why I added that, because I wanted to write it like so. R cross p, using the chain rule, is dr by dt cross p plus R cross dp by dt. See, I added this term for free. Now this is equal to that, so these two terms are equal to that, but that is angular momentum. So net torque is equal to dl by dt. Okay, so that was the derivation in Newton's second law. All right, so again, that is a pretty big result of this system, of this chapter. Okay, so for linear motion, you had Newton's second law was dp by dt, and this reduced to F equal to ma for the special case of mass not changing. Similarly, there's Newton's second law. Okay, the general case of Newton's second law for rotational motion. And for cases where the moment of inertia is not changing, this will reduce to, what will it reduce to? I alpha. Okay? And in many cases, the moment of inertia does change, and so then you have to use this formula. Okay, so that's Newton's second law. Okay. Now, this applies to a single particle, and it also applies to a system of particles. So if you have a system of particles, the total angular momentum of the system is the sum of the individual angular momenta. Okay, this guy is changing at Ti. Okay, Li is changing, rate of change of Li is Ti, and you can add up all the torque vectors, and so that is the net torque acting on the system. Okay. So this law applies for a single particle, and it applies for a system of particles. Okay. So just like this law applied to a single particle and a system of particles, just like that, then this law, Newton's second law, applies to a single particle and a system of particles. Okay. All right. The net torque is the sum of all the torques, okay? And what this is saying is this is the torques due to the internal forces acting in the system plus the torque due to external forces. And this always adds up to 0 because for every force, internal force, one internal, there's an equal and opposite force. And the torques of these guys always add up to 0. So the net torque is equal to the external torque. And here's where conservation of angular momentum. So if there's no external torque acting on the system, the angular momentum of the system will be constant. Okay, and this is very important. Okay. Now, I guess, so for instance, let me show you an application right off the bat. Right, so there's the velocity of the wind, the ball is thrown that way. Why do you throw a football with a spin? Do you guys know why do you throw the football with a spin?
Go straight conservation momentum.
I'm sorry?
It'll maintain like direction between x. So it spins, so it'll keep on track instead of flipping. It'll go further.
I'm sorry?
It'll go further.
It'll go further, but that's not the reason why you're throwing it with a spin.
It's hard to catch a badly from ball.
Okay, so the most powerful computer on the planet is the one attached to your shoulder. That's a pretty powerful thing. But you know, if the football wobbles, the drag force on it changes. Okay, the wind will apply random forces, and if it wobbles, the drag forces change, and you can't calculate where it'll land, even though you have the most powerful computer in your head. Okay, so if the orientation of the ball is the same, then you can roughly calculate, no matter how windy it is, you can calculate the drag forces where it'll land fairly good. Okay, and so that's why you throw it with a spin. When you throw it with a spin, it has angular momentum, and the forces that the wind exert, the torques of those forces are 0 because that wind force. I mean, now, if it was windy such that here's the football, on this side of the football, the wind is blowing harder than on the other side, that won't happen. Okay? Then there will be an external torque. But the external torque on it is 0. And the angular momentum will be conserved. Okay. So you can try this. This is really fun. Go to the beach on a windy day and throw a frisbee. Okay, so let's say you throw a frisbee like that and it's spinning. Looking at it from the top, it's spinning clockwise, so the angular momentum is like that, pointing downwards. Okay. And no matter how windy it is, it'll remain flat. Yeah. So very good. Okay, so that's why, so this has spectacular applications, and now we'll talk about this. Okay. So the point is external torque. In nature, the random forces that come into play have 0 external torque. So angular momentum of a system will be conserved. And that is the reason why they give spin to a satellite. Okay. So you have a satellite. When you launch a satellite is, here's a satellite. What is the satellite doing? You're bouncing signals off the satellite. Okay? You spend $500 million to put that sucker up there. Now, if a little pebble hits it, if the orientation of the satellite changed, that's become a $500 million piece of junk. How do you fix that? You give it a spin. And that little pebble won't change anything. Okay? So we use this conservation of angular momentum to our advantage. All right. Now I'm going to go through some of the slides fairly quickly because there's some really cool applications. Okay. So if you have a point particle going about as in a circular orbit at constant speed, the angular momentum of this particle about that center is mvr. Okay. Here's a rigid object rotating about the z-axis, and its angular speed is omega, angular velocity is that. Okay, so the angular momentum of this particle is mri omega, and so the angular momentum of the whole disk L is summation Li. Okay, all those vectors are pointing in this direction, so it's summation mri square omega. Omega is constant, omega mi ri square. But this is just moment of inertia, so it's I times omega. Okay, so for a rigid object rotating with an angular velocity omega about a fixed axis, L is I omega. And that is the parallel of P is m mass times velocity. Okay. So the parallel of that is I omega. Yep. So the angular momentum is I times omega, and if I doesn't change, for rigid objects it doesn't change, you can take the derivative of that. Tau is dl by dt, which will give you I times alpha. Okay. So that's for rigid objects where I is not changing. Or even non-rigid objects where the I is not changing in the motion. Yeah. We'll come to this later. Okay. So I guess I am recording this, but it will be hard for them to see this. So here's a very neat thing. Okay, so here's the wheel. Now here's the force of gravity that's acting down like that. So if you calculate the torques about that point, there's a torque which will make it fall this way. Your fingers are rotating this way, so it will give you an angular momentum instead. That fell. Now we'll change something here. So no big deal. It's at an angle and it fell. Now the same wheel and the same torque now it's precessing. And once it had angular momentum, the angular momentum was changing such that this guy was precessing. Okay. All right, so when you give this guy a spin, okay, the torque due to this force makes the angular momentum precess. Okay, the top will precess. And it turns out that, okay, this precession velocity is much smaller than this velocity, the spin velocity. Okay, now you'll think that why are we learning all of this? Here's a spectacular application of this. Okay, so if you have an object and you apply a torque on it that wants to topple it, if it's spinning, it'll precess instead. So let's look at an application of this. Okay, so here's the Earth. It's a spinning top. But what is trying to topple it? If the Earth was by itself in space and was spinning, there's no torque acting on it, and it would maintain its angular velocity and maintain its spin axis in its orientation like that forever. Okay. Now, it turns out that the gravity of the sun and the moon are trying to topple the Earth. Okay, they're trying to topple it. And because the Earth is spinning, this axis precesses. Okay, and if the density of the Earth was uniform, if it was a perfect sphere, there wouldn't be any torque. Okay, but there is a torque due to the gravity of the Earth and the Moon. Okay. Well, so this axis is precessing. Well, do we have proof of this axis, this fact? Yes, we do. Okay, so here is the proof. Yeah. Now, when they first discovered it, they, of course, didn't know this. Okay, so let's say the axis didn't precess, and the Earth's axis was spinning. Well, it was going around. It's going around the sun, but you see. Okay, so think of the axis like this. Think of so here's the Earth. Okay, so in this room, that's the sky, the ceiling and the floor and all are the sky. Okay, so I'm going to turn. This is the Earth spinning. What do I see? I see that the sky is going around. Is every point of the sky moving? What point is not moving? Yep. The points right above the pole, above the axes, are not moving. Okay. Now, if the axis precesses, then those points should be moving. The point above the axis, that's the North Star. So here's proof that the Earth's axis has been precessing. All right, so this is the North Pole, the star right above the Earth's axis today. Okay, the Iraqi people were very good astronomers. 5,000 years ago, that was the North Star. Okay, so it turns out that now this is an easy calculation. It takes 26,000 years for the Earth's axis to precess. Okay, so what does that mean? Okay, so for instance, here's the Earth's axis. In December, we are tilted away from the sun as the most, and the sun is shining at an inclined angle, and we have winter. In the summer, our axis is tilted most towards the sun. Okay, so June 22nd, we get the most heat and stuff. Yeah. So, if you go freeze yourself and come back 13,000 years from now, in 13,000 years, the axis will be pointing like that. And you'll have winter in June and summer in December. Okay? So again, so this is a spectacular illustration of the precession of Earth's axis. Okay. All right, so let me illustrate this. This is kind of cool as well. Doesn't last too long. A nice platform, it would have rotated like that. So, all right. Oh, well, I can show it. All right, so if I don't give it an angular momentum, there is the Earth's gravitational force, and it gives it a torque and just falls down, just like in the before where you saw the top window. Now the same torque is making it precess. All right, so okay, so in this problem, so I'm not going to go through the derivation. This angular velocity about the axis, that's little omega, and the precession velocity is capital omega, okay? Now, the faster this spins, the slower it will precess. Okay, so that's what this is showing you. M is the mass of the object, acceleration due to gravity, and R is the moment arm. I is the moment of inertia divided by omega. Moment of inertia about that axis divided by omega. So faster it's spinning, slower it'll precess. Yep. Now here's a very, I don't know if you guys know this, but if you drop a cat from anywhere about 3 feet, it'll always land on its feet. And I guess a fireman can tell you this, because if a cat is stuck in a tree and you scare it and drop it, it falls from the tree, it'll always land on its feet. Okay, what's going on here? Okay, we learned that external torque is equal to dl by dt. If the external torque is 0, its angular momentum will be 0. Well, the force of gravity is acting through the center of mass. Okay, you calculate the torque about the center of mass. The external torque is 0 on it. Okay, so this has 0 angular momentum to begin with before you drop it. To land on its feet, it's got to turn its feet to the ground. So how does it do that? Because its total angular momentum has got to be 0 through the entire fall. Do you guys understand what I'm saying? So angular momentum is 0. Okay, so what is happening is, to turn this way, what it does it turns its tail the other way. Okay, if it wants to spin the body this way, it has to turn the rear of the body the other way, or the tail the other way. Okay. And see, this is a serious experiment, and so we even have a video for your So what you've learned today is, through that entire complicated motion, you're able to say the following. What are you able to say? Well, a little more sophisticated statement is what I'm looking for. The angular momentum of the cat remained constant throughout the entire fall. Okay. The first 20% of the class, you learned to say that the total energy of the system remained constant. Then you graduated to saying that the linear momentum of the system remained constant. And now you can say the angular momentum of the system remained constant, okay, for an isolated system. So what you're learning to do is say more and more powerful things. Okay? So for an isolated system, now you know 3 quantities that are constant, no matter what kind of motion happens. Okay? All right. All right, we saw all of that. Okay, so we now know why we throw a football with a spin, because if it maintains its orientation, the drag forces, the effect of the drag forces are easier to calculate than if it was wobbly. If it was wobbly, the drag forces are changing, and even with the most powerful computer, you're not able to predict where it'll land. So you can go run and catch it. Okay. You've seen this system here. She's spinning initially, and then when she brings her arms in, what she's done is she's reduced her moment of inertia, because the moment of inertia reduced because now the mass is distributed closer to the axis of rotation, and so her angular velocity increases. Okay? And as long as there's no external torque, she can keep doing this back and forth. She's spreads her arms back again, and she'll slow down. Okay? And as long as there's no friction, she can keep doing that forever. Okay? What will happen here? This merry-go-round is spinning, and if this guy walks toward the center, the moment of inertia of this system decreases, just like for the skater, and it'll spin faster. And you can walk back and make it slow down again. Okay. This is very spectacular. Yeah. So let's say and I have the system here, and you're welcome to try it at the end of class. It's freaky. Okay. So what we'll do is, so she's at rest. We'll give this spinning wheel to her. So the total angular momentum of the system is that. And then she will flip the wheel. Okay. So now I'm going to do a simple drawing. The wheel is this way, and there is the angular momentum of the wheel. Well, this is an isolated system. There was no external torque acting on the system, so the total momentum, angular momentum, should be constant. So what's going to happen? It's crazy. I mean, it's very hard to, figure it out. So let's say this angular momentum was 20 units. This is minus 20 now. So what will happen is she'll start spinning, and her angular momentum will be plus 40 units. So 40 minus 20 will give you 20. Okay? So that's what's going to happen, and let me show this to you. And like I said, you guys are welcome to try this after class. Now this is not just fun. Now you know how to turn a satellite. Okay? So for instance, angular momentum is 0. I give the system like that, and I'm turning it 0. Right? I want to turn this way. Okay. If I wanted to turn on this axis, all I need is a gyro and this axis. Now I can't turn it this way, but if I were in space, I could do that. So conservation of angular momentum is really very spectacular. Okay. All right, here's something that you guys see. Now, here's this diver, okay, and there's the pool. And now you've seen this in diving competitions. Sometimes you'll have to spin twice before you hit the water. Other times you have to spin 3 times before you hit the water. And you're jumping from the same platform. So how do you do that? Okay, so what you do is, so you jump off, and there's so much time you have before you hit the water. So if you want to spin 3 times, you better have a larger angular velocity. Okay, so what is happening is the following. When you push off, so here's the weight, and you're giving yourself an angular momentum. Okay, At launch, you give yourself an angular momentum. So this system has that much angular momentum, okay? And that angular momentum is equal to the moment of inertia of that system times the angular velocity, okay? The moment of inertia is about the center of mass. Now, if you scrunch up, then the moment of inertia is smaller and your angular velocity is bigger. So you stay scrunched up longer if you want to spin more. Okay, and that's the training that goes into that sort of stuff. Okay, so you learned how to turn a spacecraft in space now. All right, I'm going to quickly go over 2 or 3 slides. These are fundamental quantities. Okay. It turns out that angular momentum is a fundamental quantity. All these microscopic particles have quantized angular momentum, and this is the unit for angular momentum. So for instance, every electron in the universe has an is spinning, and that's the angular momentum. 1/2 h bar. Every proton is spinning at exactly the same speed. Every neutron is spinning at exactly the same speed. Okay, and that's the angular momentum. So roughly there are 10 to the power of 80 protons in the universe, and they're all spinning at exactly the same rate. Okay, so particles that have half integer spin, they're called fermions. And then there are other kinds of particles that have integer spins, and those guys are called bosons. Yeah. So, for instance, the entire universe is made of these guys, as far as we know. Okay. These are the 6 quarks. They all have half integer spins. There are 4 forces in nature that are mediated by these guys, by the bosons. And these guys have integer spins. These guys are the lightest. These guys are heavier. These guys are the heaviest. These guys are unstable. Okay, you can make these guys in lab, and then they'll decay within a millionth or a billionth or a trillionth of a second. Yeah. So everything stable in the universe is made of these guys. Just these guys. Okay, just these guys. And these, okay, so these are fermions, these are bosons, and okay. So there is the unit, the fundamental unit of angular momentum. Again, like I said, all these guys have half integer spins. These guys have integer spins. Okay. Leptons these guys can only interact via weak forces. These guys can interact via all 4 forces. These guys can, okay, so leptons are weak and gravity. This is strong, weak, electromagnetic, and gravity. Okay. All right, so that's the story of the universe. You see this in chemistry as well. Okay. So here's the nucleus, and electrons can only orbit in certain orbits. Well, what's special about these orbits? Well, the orbital angular momentum is quantized. In this orbit, the principal quantum number n says the angular momentum of that is 1 h bar. The orbital angular momentum on this orbit is 2 h bar, 3 h bar, and so on. Okay? And then these guys have sub-levels. And the deal is the following. If you are a fermion, which is your angular momentum is half h bar, only 1 fermion can stay per quantum level. Okay, so that's what gives you the structure of the atom. Okay, so for instance, this the 2s orbital. Okay, so let's do the structure of lithium. Lithium has 3 electrons, 1 s2 in the first orbital. Okay, 1 tells you the orbital angular momentum. Okay, P tells you P is a So that's the one is the principal quantum number. S tells you that's the that's no, that's the orbital angular momentum. So n, that's the principal quantum number, and then S, P, D, F, those are the angular momentum numbers. Okay, so S corresponds to 0, 1, 2, this is 0, 1, 2, and so on. Okay, and for each level you can be spin up or spin down. Okay, so for this principal quantum number, you can have in spin up or spin down. So you have two electrons there. You can have two electrons here. And the next level is 2s. You can have two electrons, but there's only one electron. So total of 3 electrons. So there's the structure of lithium. Okay, the structure of sodium, for instance, 2, 8, and 1. Okay, so the structure of sodium is 1s2, 2s2, 2p6. So there's the electrons. So p orbital has px, py, and pz, and each level can have 2 electrons. So there's 6 electrons, and then 3s1. All right. So that's, again, in one quantum state, you can have only 1 electron. And so that's why all the electrons are not in the lowest state. That's why their electrons are in higher and higher levels. Okay. All right, so here is another spectacular example of conservation of angular momentum. So to give you a scale, if our solar system is as big as this room, okay, so the sun is at the center and the furthest planet is at the corner of the room, okay, this solar system was formed from a cloud as big as this campus. From Dunn Avenue to White Street to Clyde Morris to International Speedway Boulevard. So that cloud collapsed into a tiny ball, which is the sun. 99% of the mass is in the sun. Okay, so and that cloud was initially spinning, just like a skater was spinning. What happens when the skater brings his or arms in? You spin faster. So as the cloud collapsed, its angular momentum remained constant. Okay, so now you can say something that has remained constant for the last 5 billion years. What has remained constant? The angular momentum of the solar system. Okay. You saw the Earth's precession. Okay. Okay, so now here's the deal. Here's a proton and here's an electron. So you go to a store, buy a proton and an electron. I'll make up these numbers. This is roughly. So if this guy weighs 2,000 units, this guy weighs about 1 unit. If I make a hydrogen atom using these two guys, how much does the hydrogen atom weigh? You guys can add? Huh?
I couldn't hear. 2001?
2001. You've been to college and very smart answer, 2001 units. Okay, it doesn't. It weighs less. Okay, anytime you form a bound state, it weighs less. If you tried to bring 2 protons together, they repel each other, they would weigh more. Okay, a bound state weighs less. The harder they're bound, the less it weighs. Okay, so for instance, okay, what I mean by that is, okay, make sure you guys understand this. This is very important knowledge. It won't, and that's why it's not on a test. All the important stuff is not on the test. Okay, so here's a proton, here's an electron. Here's a proton and an electron in the third orbital. Okay, this guy weighs less than this guy. This guy is more tightly bound than this guy. Okay. Well, how much less does this guy weigh? 13.6 electron volts. Okay. All right. Anyway, you guys understand. The more tightly you're bound, the less you weigh. Okay. That's how stars produce energy. Okay. So, for instance, at the center of the star, at the center of our sun, the temperature is 15.6 million degree Kelvin, and so on. Okay, so what this is showing you is the following. At the center of our star, what we do is we combine 4 protons and make a helium nucleus. And in the process, 2 protons got converted to neutrons and stuff, but we won't worry about that. But this is a very strongly bound thing. And this guy weighs less. Okay? So he weighs less. So there's the mass of 4 protons, 6.69 times 10 to the minus 29, 7 kgs. And the mass of 1 helium nucleus is 6.64. See, it weighs about 1% less. Well, you took these ingredients and cooked something, and this guy weighs less. Well, what the heck happened to the mass? The missing mass? What?
Got lost to energy, heat.
That's what got converted to energy, okay? That's what Mr. Einstein says. So that's how the stars produce energy, okay? And that comes out as radiation and stuff like that. So the sun was born 5 billion years ago. Let's say when it was born, if it was 100 pounds, by the time it dies in another 5 billion years, it'll weigh about 98 pounds. So the sun will lose 2% of its mass roughly. Okay? All right, that's what this guy is showing. So a bound state weighs less. Okay. So what we are saying is, so let's say each of these guys weighed 100 units. Now this entire thing weighs less, about 1% less. So the mass of each one of those is 1% less. Okay, so each of those guys weigh 99 units. What if it was bound stronger? Then they would weigh even less. Right? You guys understand? That's what this graph is telling you. Here's the mass of a free proton. In a helium nucleus, it weighs that much. Okay. Look at that. In carbon, it would weigh even less. So, you want energy, take a whole bunch of helium nuclei, squeeze them into carbon nuclei. You get energy. Well, you're greedy. Take a whole bunch of carbon, squeeze them into iron nucleus. You get energy. Now, if you want to go beyond that, well, you have to put energy now. They're not as strongly bound. So, all these guys were made at the heart of stars. Okay. Now, if you want to make this guy, all these guys, you have to put in energy. And now let's see how that happened. Okay. So, this is fusion reaction. Okay. And now in our fission, in nuclear reactors, we take, we take these heavy nuclei and we split into smaller nuclei and get energy. Okay. All right. So what this is showing you is the following. Okay. Okay. So here are the numbers. About 10,000 degree Kelvin, hydrogen fuses to helium. So to go from hydrogen to helium, you need about 15 million degree Kelvin. You want to go from here to there, you need to be hotter. You need about 100 million degree Kelvin. You go to helium to carbon. You want to cook something even larger, carbon starts fusing and other fusion reaction occur till if you're above 600 degree Kelvin. Okay. So at the center of a star, Okay, so here's a star. Okay. What do these guys want to do? They want to fall down. All these guys want to fall down. How do you prevent these guys from falling down? You produce heat, and this energy exerts an outward pressure, and you're holding stuff down. Okay, so you got to keep producing heat, which you're doing through nuclear fusion. Okay, and once you run out of hydrogen, you can't produce any more helium. Then stuff starts collapsing. This gets hotter, and more other reactions start taking place. Yeah? And you're producing heat. What, after all this turns into iron, what happens? I'm sorry?
Fusion stops.
Fusion stops. Very good, my friend. You're not producing any more heat. You can't prevent this guy from falling down because you don't have any more heat to produce. Some of this stuff collapses. It bounces off this core, bounces off, and it collides with this falling outward falling stuff. You get an explosion like you've never seen before. That's a supernova. And in that energy, you produce heavier nuclei. So in the supernova explosion, you produce heavier nuclei. And now, lately, in the last 20 years, we've also realized that colliding neutron stars also produce heavier nuclei. Okay, so that's where all the heavier nuclei come from. Okay, so here's a simulation of so 0 milliseconds. So 0 milliseconds is when you, at the core, you've reached iron. Okay, and the inner core falls. The stuff outside the core falls, and then it bounces back, and you get a supernova explosion. Okay, so if the once iron is reached, no more fusion energy is released to maintain its internal temperature to apply outward pressure to hold up the star. The core collapses in the span of a second, about a second. The outer layer fall in and bounce off the collapsed core. So the bounce off and then colliding with the outermost stuff produces a supernova explosion. If the core of the supernova has a remaining mass greater than 1 point solar mass, the compressional force of the supernova explosion are great enough to force protons and electrons to combine and making neutrons. Okay, so the core becomes a neutron star. Okay, so the final stages of the death of a star. So this is a solar mass. If your mass is less than 1 point, if the mass of the core is less than 1.4 solar masses, then you're a brown dwarf. That's what you die as. You just become a piece of rock. If your mass is between 3 solar masses and 1.4 solar masses, then you're a neutron star. Okay, a neutron fermion pressure will hold you up. Okay, this is being held by electron pressure, but again, that's a story for another day. If your core is greater than 3 solar masses, then you become a black hole. Okay. All right. One last thing. So here's a star collapsed. Okay, a star roughly between 2-3 times the size of the sun eventually can collapse into a neutron star as it runs low on fuel. The radius of the star decreases by about 1 million kilometers to a few kilometers. So the radius of the sun is about 700,000 kilometers, and our sun won't become a neutron star, but if it became a neutron star, its radius would be about 10 kilometers, roughly from here to Ormond Beach. So imagine a skater compressing that much. The spin rate would increase tremendously. Okay, so neutron stars are rotating about 1,000 times a second, 1,000 revolutions a second, a massive object like that. All right, so here's a neutron star. Okay, so imagine this is rotating 1,000 times a second. And the neutron star is along its axis, it's emitting particles. Okay. Particles are escaping along the particle axis and radiation as well. And if this happens to be pointing at you, if your Earth, once every 1,000 times a second, you got a beam shining at you, like a lighthouse. That's how neutron stars were detected. All right. So our sun rotates about 1 revolution per month. Okay. But when the sun will collapse, its rotational speed will increase. Okay. All right, guys. So we will stop here.